great applause to welcome Tapo.
Thank you so much, Ethan, for such a kind introduction. Hi everybody, I'm super excited to be here. Thank you also to the organizers. I was thinking about this, and I was telling a couple of people yesterday. I have actually, in the US, I've never really seen an event like this, where different universities, like the students during their graduation, they show off their projects, they come together. It's like it's a version of capstone demonstration that we have in the US, but on steroids. Like it's much larger scale. It's fantastic. Also, it was great to see the Wildbot competition. Lots of fun. Really. Cool. So I think, as Ethan mentioned, I work in this area called assistive robotics, particularly physically assistive robotics. What that means is robots that have to touch people to assist them with day-to-day activities. Activities that maybe they cannot do by themselves. So our target population are people with disabilities, old age people, because of that, they won't be able to do these tasks, right? So with that, my full name is Tapomayukh Bhattacharjee. You can just call me Tapo. There is the lab, and you can check out the lab for more details. Cool. So all the work that I'm going to present are done by my fantastic students here. I am just presenting on their behalf. So the credit goes to them, right? And as you can see, we love to eat, and eating is also a part of our research, which you'll see. So the way I'm going to give this talk is I'm going to first bring us to the same page of why this area is important, and also why this area is hard. It's very hard to do, right? First, physical caregiving is very multifaceted, and it's also contextual. What do I mean by this? There are various tasks. These are in occupational therapy. These are called activities of daily living. People, like caregivers, helping care receivers or recipients with eating, bathing, toileting, getting dressed, getting around, or getting in and out of bed with transfer. There are also various other IADLs, instrumental ADLs, right? And it's very multifaceted because there are so many different tasks, which means you have to be able to give assistance for all of these different kinds of tasks. You have to generalize to different tasks, which makes it very challenging, right? But it's not just about tasks. In robotics, generally, generalization to tasks, every roboticist talks about it. It's like the holy grail, right? But in physical caregiving, there is something more. It's also about the users. Let's look at this. Here you will see both the users, the left and the right video, they are being assisted with feeding because they cannot eat themselves. They cannot move their arms. On the left, this person moves their neck a little bit. His mom, who's the primary caregiver, brings the food close and he bends his neck to eat. On the right side, Henry, he can only chew food from one end of their mouth. So the caregiver has to very carefully place the food under their left molar. So the same task, feeding, but because the user is different, you have to give the assistance in a very different way. So again, it's very multifaceted and contextual, right? It depends on their functioning abilities. Is it just about functioning abilities? No. Users can have different behavioral traits. Tyler on the left loves to eat while watching baseball or TV. Henry shows his intent to take a bite by looking at the caregiver and opening the mouth. The caregiver has to understand the intent and then feed. It's not just the users, it's also about their environments. The same task of taking Henry up. When there is no cellar lift, caregiver just lifts him. But on the right, the caregiver uses cellar lift and then pushes, taps his knee, like around the knee, so that he doesn't have spasm to be able to get up. Again, depending on the environment, the same task you are doing in different ways. Finally, also different caregivers. The same dressing activity. William is strong and muscular, can lift the leg. Jane, who is his wife, does the same task in a very different way. So what I'm trying to tell you from all these four slides is that caregiving is very multifaceted. It is dependent on the user, it's dependent on the task, it's dependent on the environment where the user is, and it is dependent on who is giving the assistance. So if we want robots to be able to assist, they have to generalize to all of these different things. That's why this is hard. Especially because my home is going to look very different from your home and your home and your home. And your home is going to look different from morning to evening to tomorrow. That's what makes it different, right? Okay, so then the first question. Do we actually need robots? Maybe there is a different solution for this. So instead of bombarding you with statistics, you can just Google in the internet and find statistics. There is a huge lack of human caregivers. It's a big problem, aging society. Many presentations will say that. But for me, instead of saying that, I am going to just show you the lived experience of the last 6 months of one user. Okay, let's read together. As a quadriplegic, my daily survival hinges on reliable and competent care providers. Yet in the last 6 months, I have cycled through 4 caregivers, each departure plunging me into crisis. For example, after one provider left, I had no choice but to pay $300 for an accessible rental vehicle and transport myself to the ER, emergency room. In nursing homes or hospitals, I often face additional risks, including neglect, the destruction of my adaptive devices, and the financial strain of losing most of my income to institutional care fees, leaving me unable to pay rent or utilities. The lack of continuity in care repeatedly uproots me from the only environment equipped to maintain my health and independence, is their own home. A robotic helper designed to assist with critical tasks like catheterization, bowel care, and feeding would provide an infallible safety net. Such technology would not only save me from the dangerous and costly spiral of emergency interventions, but also restore a sense of stability and autonomy in my life, preventing the preventable and ensuring my basic needs are always met. This is why me, our lab, and various other labs in the world are working towards this. We are still far from this reality, but we are taking small steps towards it. Now, if we want to bring robots into these people's homes, for all of these cases, the same issue, right? It is contextual on the user, the environment, the caregiver, and the robot. But the central message is here. This is why it's extremely challenging. Caregiving, as roboticists, we want to have a robot that generalizes, that builds a system that serves everybody, all of you. But a person will never accept the robot for long term if they don't feel like the robot is just built for them. There needs to be a personal connection. So this trade-off between generalization and personalization, it's a huge trade-off that my research and focuses on, and you will see this theme across various projects. Cool. So then the question is, this field, physical robot caregiving, did I invent this? Did I start this? No, of course not. It has a huge history. Actually, around 1960s, one of the first manipulators, Rancho manipulator, around 1963, was developed. It was controlled using tongue. It was controlled using tongue. To do, like pick up a glass of water or things like that. Around 1970s, one of the first robots to help people with visual impairments to navigate, like Meldon, came up. Around the same time, there was a Moorwood spoon lifter from this company that was developed that was used to pick up food and feed people. Towards 80s and 90s, multi-purpose robotic systems started coming. This robot arm workable system could do some meal preparation, cooking, handy one. You can use handy one to do toothbrush, like brushing, eating, as well as picking up things. But the issue with all of these things were, they were pre-programmed, there was not much intelligence there. So when you tried to deploy them, they did not work. Because, as we saw, it is very contextual. One of these particular applications, the feeding application, got a lot of attention. And around 90s and 2000s, a lot of companies started developing their feeding devices. Okay, I remember around maybe 16 or 17 devices started working on this. A couple of companies were there for transferring people also, like the Riva robot, right? But what happened? Again, there was lack of intelligence. And so, the people bought it, they stopped using it. Around mid of 2010s, that's when academic labs started putting physical intelligence or intelligence into these assessment devices. Like my lab is one of this. Like this particular picture is Professor Eating's work, right? So there are various labs that are working on this around the world. And fun fact, today, out of all those 16 companies that we saw, only Meter, Eater, and OB remain. And even those companies, there is not much retention in the user. So the point here again is we need physical intelligence for these devices to go to people's homes and generalize as well as personalize. And this is where my lab comes in. Specifically, this is what my lab is. We try to develop full-stack physical robot caregiving ecosystems, where on the top, there are various applications. Robots feeding people, robots bathing people, robots dressing or transferring people from bed to beach. Now to support them, we work on various algorithms. And on the bottom layer, what I call are toolboxes that we have developed. Open hardware, like skin sensors, open simulators, software libraries, and data sets that are being used by multiple groups around the world. But even if you don't remember anything from my talk, this is the key insight. We, just as engineers and computer scientists, if we just develop these problems or solutions for these problems in our labs without talking to stakeholders, we will inevitably tend to invent problems that may not be useful in the real world. We can publish papers, but it will not be useful. That's why it is very important to have this stakeholder input continuously. And what I mean by stakeholders, people with disabilities who actually need this, caregivers, occupational therapists, healthcare professionals, all of them. In our lab, we have weekly, bi-weekly meetings with these to be able to do this. They tell us what problems to work on, and what are we doing. Okay, so with that said, let's dive into some of the technical aspects of how we have developed these systems. We have been able to develop some of these systems and deploy these in people's homes, in hospitals, as well as in the lab. It's not possible for me to cover every project. I'll cover some of these projects. And I will cover this in a high level. If you have any questions, I'll be very happy to answer. So let's get technical. Now, physical robot system, caregiving system, what is unique about this is the word physical, which means contact. Robot has to come in contact with the person, right? So, contact in physical caregiving varies across contact states. From localized contact, like when you eat, where only the tool is coming in contact with your body, to whole-arm contact, like in the middle, to whole body, like whole body contact. And both the hardware and software need to evolve as you go from localized to whole-arm to whole body. So let's look at each of these. Localized contact. As an example, I'm going to ground this to the application of eating. This is how it looks like, our robot. It's a robot arm mounted on a wheelchair. Everything that you see is autonomous. It picks up a fork. We have done work with chopsticks, we have done work with spoon. It can pick up a tool based on whatever is needed. It goes on top of a plate. It looks at the food items, algorithms tell what food items it is, how to pick it up. Then it uses both visual and haptic feedback to pick up the food without destroying it, and then goes in front of a person and then aligns it so that it's easy for the person to take a bite. The system is divided into two parts. Bite acquisition, which is how do you pick up food from the plate, and then bite transfer, which is how you transfer food into somebody's mouth. So let's look into each of these. By the way, this person does not have a mobility limitation that we know about. So this is just an actor. Okay? But I will show you later how we have actually deployed this with people who actually need this. Okay. So let's look at bite acquisition first. So for bite acquisition, we have been able to pick up a wide variety of food items, meals, that we just went to, in Ithaca, where Cornell is, there is a chain, weapons. We just went, bought store-bought food, or someone home-cooked food, put it on the table, and the robot is able to pick up while catering to users' preferences. How did we do this? Here is the idea. The robot has a sensor, a camera, on its wrist. It's looking at the camera, like looking at the plate. So let's say on the left there is a plate. It gets passed to a visually conditioned language model. It's a foundation model, if you have heard of this. How many of people here have heard of foundation models? Okay. Think of this as large, like, okay. How many people here use ChatGPT? Okay, anyhow. ChatGPT is an example of a foundation model, but it's only language, like, or predominantly. Now imagine I also give, in addition to language, I also give image to it. That and the same idea for visually conditioned language model. Okay? So that is a VLM. The output, what does the VLM output? It says two things in this case. First, what food items there are in the plate. Second, where are they in the plate? Okay? That information goes to a structured task plan that you see with a symbol that is similar to T, tau. What does that do? It tells how many actions or skills do I need to pick up. So for example, if I were to pick up the meatball, I can just skewer it. One action. Skewer, I pick up the meatball. But if I have to pick up the noodles, I have to first push the meatball and then pick up the noodles. Two. Okay? So that tells me what is the sequence of action I have to take or skills I have to do to pick it up. That goes to a downstream LLM. LLM is an example of a ChatGPT. This takes that information and a user's input. User, let's say, who's on the wheelchair, just suddenly says, I don't like meatballs, so please don't feed me meatballs. Just feed me the spaghetti. LLM uses that information, both of this information, to figure out in what sequence it should feed. So let's look. Right? Here, the person says, please don't feed me any meatballs. Now the robot goes, it's trying to push the meatball. It failed. It will keep on doing this until it succeeds. Once it succeeded, the robot will twirl the noodles and pick it up. Next time, it figured out there is not enough noodles to pick up. So it's going to group them together, and then when there is enough noodles, again it is going to twirl and pick it up. Okay? That's how it works. So then the question is, did we solve eating? Done? Robot can pick up everything? No. So many failures still happen. Imagine all the kinds of food that we make. Some are soft, some are slippery, something's like, because of many reasons, robots still keep failing. So we went back to drawing board. We were like, okay, this is pretty general. What else can we do? We tried various things. First thing we thought, maybe the robot doesn't know how to pick up because it doesn't know that I have to go like this to pick it up. Like action space is not good. So we thought, but can I keep trying? Like if you ask a baby, if you give something to a baby will keep trying to pick it up. But if it falls down, it's okay, it will keep trying. With food, if I have a fork and I don't know how to pick it up, I am trying in every way, food will get destroyed. I cannot keep trying this, right? But if I can create a simulation environment on the fly, then I can try it. So that was the idea. Plate is given, I look at it, I immediately create a digital twin in the sim. Now in the sim, the robot is practicing. And once it succeeds, then it executes in the real. That improved the success. Still okay, not so much. Here we started looking at, okay, let's not just rely on vision. We also, because similar food items that look similar, they may need different strategies because some may feel hard, some may feel soft. Let's look at haptics, the feeling of touch. We tried that. That improved the success rate. Still not enough. What we realized was that when we want to deploy these robots in all of our homes, there will always be an edge case where these algorithms will fail. Always. Which means we always need to have humans in the loop. So this is where we went and we developed a human in the loop algorithm to be able to do this. Even with all the autonomy, robot autonomy, when it fails, let's ask a human. The question then, the point is, how do we decide when to ask a human and how to ask a human? And there, the point here is that if our strategy is like this, oh, robot has some way of telling, oh, I'm not sure, can I pick it up? Let's just ask the human. Let's just ask the human. If the robot keeps on doing it, will you use that robot? Imagine during a meeting, it's continuously asking you. You will feel annoyed, right? Imagine your phone is continuously pinging you, asking for help. You will not use the phone. So, we have to consider what is the effect of the query on the human. So, will they get annoyed? We started talking about this using something called a query workload. What is the load on the person when the robot is asking? And can the robot optimize for that? Okay? That was the key insight. So, using this, we developed this algorithm. Ignore everything here. Basically, the idea is this. If the robot can take all of these different actions, it has this idea in the algorithm, what is called uncertainty. How confident I am in picking up. The way we measure this is the lower bound of the best action and the upper bound of the second best action. That is our measure of uncertainty. And we compare this with the workload model that we have developed by querying hundreds of users and developing a model. So using this, now what happens? Look. What happens is, on the left, we have this person, right? This person does not have a mobility limitation. And whenever the robot fails, the robot is asking the user. Now on the right, this person has multiple sclerosis. Okay? And what happens is, even if sometimes it fails, the robot is not going to ask the user because it knows every query I am asking with this person with multiple sclerosis, it's very difficult for them to respond to it. It only asks them when it's critical. Now because of that, what results is that this way. It may take 10 more minutes to empty the plate, but the user likes the robot. The user gives it a thumbs up and says that it satisfies the robot, like their perception of what they would want a behavior for a robot to be. And turns out, it goes beyond this. We actually deployed this in the home. This person with multiple sclerosis, this person with spinal cord injury, as well as multiple people in the home. And turns out the same principle holds, right? Which is, whether the failure comes from perception or planning or whatever, let's consider not only task uncertainty, but also the human's effect. Like what is the effect on the human? So that the algorithm can balance between the two. Okay? And not just shove autonomy on top of the person. So once we learned how to pick up the food items, then we thought, okay, now we have to bring it to the person's mouth. And this is an extremely challenging problem. And I'll tell you why. Just look at this. This person with spinal muscular atrophy has very narrow mouth opening. Which means the robot, there is no way for the robot to feed without touching the mouth. Right? You think about self-driving cars. Self-driving cars moving around. There is no contact, right? You are avoiding. We think of, in robotics, generally we think of robots avoiding humans. There is no way to avoid the human and feed this person. You have to touch. Schizencephaly. She has weak bites. Person with arthrogryposis can only chew food from the left of their mouth, left side of their mouth. If the robot feeds here, they will not be able to chew. Person with multiple sclerosis has spasms. You know what a spasm is? It's not voluntary. Suddenly their body moves. If you have worked with robot, imagine a robot with a fork coming towards you and suddenly you move and you cannot control. Imagine the danger. But you have to be able to, we were successful in feeding them. How? Two key insights. First, extremely fast mouth perception with even under occlusions. Because when you have to perceive the mouth even just before the food goes in. Which means the robot itself is occluding the mouth. Right? The camera cannot see. So even under occlusions, extremely fast mouth perception. And this one is physical interaction over control, which means identify what happened and then have a controller that adapts it. To give you an example, to tell you how subtle this is, right? Now imagine that person with arthrogryposis, right? And then person with multiple sclerosis. Now robot came and suddenly when the robot is feeding them, the person has a spasm, like this, they move. The robot has to be very compliant, means it cannot hurt, it cannot be stiff. It has to be compliant so that as they move, the robot moves with it. So that it doesn't hurt the person. But it also needs to understand that was not intended. They have to forget about it. But on arthrogryposis, when the robot feeds them, let's say they use their tongue to move, to guide the fork, to say that the robot needs to go from the right side to the left side because they cannot chew on the right side. In this case, the robot has to understand, yes, it has to be compliant, but it has to understand. It has to comply because the robot, this Innova robot, it's like 30 kilograms, 25 kilograms, something like that. Moving this with a tongue. And then it is intended contact. Robot needs to understand that, oh, the person actually meant it. So next time I should not feed here, I should feed here. These kinds of subtle interactions are very important for the robot to understand. Right? So once we did that, we were able to feed people, all of these people, different levels of spinal cord injury, multiple sclerosis, cerebral palsy, schizencephaly, arthrogryposis, in hospitals, in New York City Presbyterian Hospital, in their home as well as in our lab. This is one thing I want to show you from the hospital. This was this girl from schizencephaly. She had a schizencephaly, and her father is here, and mother is in the background. If the sound is hear this? The mother started crying. The first time she felt like the person was able to eat, like feeling of independence, right? So this is it. Still not ready to be able to deploy for long term. There are other things to do here, but this gives shows us that there is a path forward. So with that, we decided, okay, we have everything that is needed. Let's actually deploy this in home, in somebody's home, for a long, when I say long term, it's still not long term, it's still a week. Right now in summer, we are planning to do this for a month. What changes in real homes? This project took us 2 years to do this. Why? It's this. First, there were a huge variety of user requests. Just with 17 people, we had 46 different requests that they want to personalize just for this one task. Impossible to pre-train. Whatever large models you have, it's impossible to pre-train in the lab. You have to have on-the-fly personalization. As you interact, the robot needs to be able to personalize. First. Second, there are many known unknowns. So how do you know these unknowns? Like things that can happen in the home that doesn't happen in the real world, or like in your lab. You have to observe. We observed these people for a long time, and we tried to figure out a list of known unknowns. That is still okay, but what we found was many algorithmic safety assumptions break. We had to do systems level safety. It's called the Swiss cheese model, with different layers of safety. Finally, this is the most difficult thing. Unknown unknowns. When you observe this, there will still be cases that you have not observed. That may happen when you go to a real home. Like suddenly a child may walk in. Child may suddenly turn off the switch, and then it's dark. And your camera, all your algorithms, oh fantastic with camera feed. But there is no camera feed, it's dark. What do you do? This is where you have to understand that failures will happen. How can you still be safe? Last line of defense must be physical, hardware safety. But the hardware cannot hurt the person. Right? So, we actually use this. So first what we did was we did this needs assessment, as I mentioned. We did the formative study, and these were, look at all of these. So many different requests from people that we got, right? Just for this one activity. Using this, we basically developed our system according to IEEE standard for transparency and ISO 13842 safety requirements. Even with our system, FEAST, which is our system, we were only able to cater to 36 out of 46 requirements, personalization requirements. And the safety was such that we had different layers, but the final layer was using the known unknowns. We prepared the safety watchdog, which is like a set of 60 to 70 rules. No command will be executed unless it passes all those 60, 70 rules, including sensor drift and all of these aspects that happen when you put in the real world. But even under that, the fork was designed in such a way that if everything fails, it cannot physically hurt. After some time, the mechanical structure, it just breaks and folds. It does not drop on the person. So with that, we actually deployed this in the person's home. Now you can see, for this 1 week, this person, like right now, do you see that dot? This dot, I don't know if you can see it. This is how they communicate with the digital world, this person. They have a nose tracker. They have a tracker on their nose. As they move the nose, that's how it points to different things, and that's how they talk to with the digital world, right? Because as you can see, talking directly is challenging for them. The robot, like first they are personalizing, now the robot will start like feeding them, like drinking, eating, as well as wiping, mouth wiping. In the entire week, 2 interventions were needed from my students. One was that they had to heat. So you saw my student come in, and then he took it to the microwave to heat the food. And second intervention was their nose tracker hung. So my student had to restart this interface. Other than that, everything, the robot was able to feed them like through every day the meals for 5 days. Now we are doing this for 1 month. In the interest of time, I'm going to move ahead and very quickly cover 2 other things that I mentioned. The first one, as I mentioned, was localized contact, like eating, right? Now let's move a little bit to whole arm contact. Whole arm contact, again, both the hardware and software needed to evolve. So here, you will see this robot. It's a mannequin. The robot has a whole arm skin that we have developed, Wi-Fi based skin that we have developed. It uses this to turn this mannequin, right, using one arm. We call this tactile and vision condition contact centric control. So the idea is for this to be able to transfer people, pick up, and things like that. This project is not as mature as our eating because we have not deployed this with people in their homes, only in the lab so far, but we are working on it. So how did we do this? There is another thing that I mentioned. You can also use this to lift. Like this is a mannequin to lift the arm. This mannequin is at the weight of average human. Right? So it is built around 3 core contributions. I am going to try to give you high-level insights about this. Don't worry too much about the technical, that if you don't understand, or feel free to ask me. First is context-centric representation. What does that mean? Basically means representation means how we as people perceive the world. Like I am now seeing humans, chairs, colors of different things, shapes of different things, right? Robots also try to make sense of what they see using their camera. That's a representation. We want to develop a representation that is contact-centric because that's where physical caregiving is needed. How do we do this? We use multiple sensors. RGB, which is like your normal camera, depth. We also use proprioception, which is joint encoders of the robot. Tactile from the whole arm skin. And based on this, we develop a proximity mask. We pass it through different encoders for different modalities, and we create a latent space. Imagine this as a smaller dimension of the entire world, right, that we have seen. Using this, we develop something called an action sample, which means robot can take many actions, right? It can go this way, it can go this way, it can go this way. How do I know where to go? How do I sample? Should I try this way, or this way, or this way? This part tells me which one should I try. Okay? That's the whole point, while making sure it's safe. And then finally, when I try different actions, which one is the best action? This is where, typically in robotics, you just use latent state rollouts. What we did was, we did latent state rollouts plus kinematic rollouts, combined the hybrid scoring, and figured out the best possible way to do it. This turns out, this hybrid rollout scheme actually helps with traditional like world models like VJPA2 and other things that are there. It also helps improve their performance at this hybrid rollout score. So, because using this, the robot was able to do well turning, lifting, and things like that. Now, as I mentioned, personalization, right? Using tactic, we generate contact-aware reference trajectories, but how do you personalize? Suddenly somebody says, like, imagine a robot is trying to touch you all over and then turn you. You all may have preferences. Don't touch me here, or apply less force. How can the robot adapt? That's the idea. So tactic, what you just saw, gives you a trajectory, contact trajectory, and then the person says something. I don't like it, or apply less force here, or don't touch me here. Then it updates the trajectory using priority touch. How do you do it? The key idea is this. First, we did a study with 94 participants where we just figured out, okay, where do people generally like to be touched? And how much preference should it give? Like, how much forces should the robot apply? Of course, every person is different. So this cannot be the result. This is just the prior, initial state. Now, what happens is, when we do this with a real person, again see the skin, this is what happens, okay? The person suddenly says that, let's say, second, yeah, the part, when it touches it, it's touching all over the body, right? Over there. So let's say the person says, like it's in the real world, the person says, please apply less force on my abdomen, or something along these lines. Robot cannot keep exploring. What if while exploring, it will hurt? Robot moves to a safe configuration. It creates a digital twin on the fly, and it doesn't have to be a good visually realistic digital thing, because the only thing we care about is contact. Now in the simulation, we developed this algorithm to try out various hierarchies. This is a hierarchy of controllers. This is the action. This is the novel part here. But anyway, when we try this, in the simulation, let's say it figures out, oh, given the person says, don't touch me here, I should move this way to make sure I still can do the task without hurting the person. And then it converges and it will do this. Turns out when we do this with people, many people prefer this. And this is not just for this. You can also get this behavior using the same algorithm, this kind of snake-like behavior, like where you go in cluttered environments. The whole point is, it's not about obstacle avoidance. That's contact and like touch, right? Finally, moving to whole body interactions, which is like, for example, transferring a person. These robots, even if they do all these things, they cannot lift a whole person, right? Like it's very heavy, person very heavy. So what we did was, we first converted all of these assistive devices that occupational therapists, that caregivers actually use in nursing homes and in homes and other homes. The wheelchair, this is the patient lift. We added actuator, sensor, and drivers to make all of them robots. But they don't have the intelligence is on the robot side, but now they become instrumented agents. Once we are developing this as a kit. It works for many different, 3-4 different top wheelchairs companies in the US, patient lifts as well as hospital lifts. Once we did that, now robot does dexterous manipulation, like tying the sling to the hook, working with the, and then everything that you see here is autonomous. This is a heavy mannequin. It goes on every side. Now the wire spring will go closer so that the robot can reach that part. Then the robot again picks up the sling, hook, and then the wire spring and the robot will work together so that it can tie. Once all the 4 hooks are tied together, then the wire spring will lift the mannequin and then work with the wheelchair so that they are aligned, and then gently drop the mannequin so that they can. So a person who would not be able to be lifted can be done this. The robots have done this with me, with my students, but we have not done human subject studies yet. We are doing this soon, right? So here you see, for example, here, robot here, speaking up, and then it's going to align it to the wheelchair. Okay, one shameless plug. We do this competition, just like Wildbot competition. We do this competition where in ICRA 2025, we do a physical caregiving competition. So the first round, in ICRA 2025, there are 56 teams from 17 countries participating in phase 1. It was simulation phase, using a simulator that we have developed for people with disabilities. And it was 2 tracks, robots dressing people, robots bathing people. 5 teams advanced to phase 2, real world, where we brought our staff to ICRA, and they came to ICRA to participate. Because of visa issues, it was in Philadelphia. It was in the US, Atlanta. But because of visa issues, 3 teams could make for the dressing and 1 team for bathing. The winner was the Brazilian team and the UK team was the winner. And each winner's got, one winner got a Innova robot arm for free. The bathing team got a stretch robot for free. Thanks to our sponsors. We'll hopefully do this again in ICRA 2027. So please participate. Okay, so here is basically my conclusion, which is based on our experiments. Like we have developed a recipe for deployment. First, we leverage foundation models, these large models, but we want to create context-centric and user capability aware representations. That's what is important. We use simulation in the loop for exploration and human in the loop for failure recovery. But when we do human in the loop, it's very important to understand. Let's not use humans as tools for robots. Let's consider human factors as very important when we develop these algorithms. Workload, their engagement, their agency is very important. Second, engage with a diverse set of stakeholders from the beginning, not when you have developed the robot and now it's time to do user study. From the beginning. And studies outside the population are informative. The generalization versus personalization. We generally develop out-of-the-box generalized system, we train it in the lab. Then we always do a calibration when we bring it to a person's home, and then do on-the-fly personalization. And there, you need flexible interfaces. It's extremely important. Somebody may not be able to talk. You need to have an interface for them to be able to communicate with the robot. Some people may use snip and puff. Some people may use chin tracker. Some people use head tracker. All of these things. It has to be a versatile system. And transparency. The person needs to understand what the robot is doing. So if the person asks question, the robot should say what it's doing. This happened in our study. One time, the person said, can you wait for 5 minutes before, not 5 minutes, something, he said, sometime before feeding me. You have worked with ChatGPT. Sometimes ChatGPTs hallucinate, right? And that's exactly what happened. The robot did not follow it and started doing something else. And the person was like, that's not what I asked you to do. Why did you do this? And the robot was able to explain through its traces what it did. That helped the person change his prompt so that they can personalize the robot to its behavior. That's why transparency is very important. What is the machine doing? The user should understand it. Okay? Finally, modular hardware and software is extremely important. End-to-end system have their place. So far, not in physical caregiving. It's my bias. I'll tell you why. Another example. One of the users, we were trying to feed them. She just refused to eat by the robot. Suddenly she said, I don't want to eat. And we were like, what is going on? Why the person doesn't want to eat? We asked their caregiver. The caregivers always accompanied them during the experiments in the hospital. The caregiver said, she just does not want to eat if the fork is like this, how generally people hold. The fork has to be inverted. Imagine, because with many physical limitations, sometimes there are associated cognitive limitations. So they have idiosyncrasies. One user said, I will not eat if the plate is placed here. Plate has to be placed somewhere else. These kinds of on the fly, there was no way for us to train for these things, we didn't know. Modular hardware and software helps with on the fly change, directly changing this, and the robot still works. If you want to make this work for many different robots, extra degree of freedom on tools really help, because it helps you generalize, because otherwise the kinematics for different robots are different. And finally, safety guardrails are extremely important, because all of your algorithms, however sophisticated and cool they are, they will break when you go to the limit. This is basically my vision. The goal is not to replace human caregiving, it's to augment human caregiving. And even like current LLMs, we have this benchmark that we released. Achieve only 53.1% success rate on typical caregiving benchmark that we developed with occupational therapists. Even at the high level, forget about the action. So we have developed various tools to build these kinds of high-level contextual reasoning, but it's a work in progress. So yeah, physical caregiving is multifaceted and contextual. Here is our lab, and yeah, thank you.
Thank you so much, Tapo. Thank you so much for a wonderful talk. And